lecture, we are going to discuss about material balance in unsteady state conditions. So far we have done material balance in steady state conditions with chemical reactions and without chemical reactions. That is material balance in unit operations and material balance in reactive system we have discussed. Now in recent syllabuses of in competitive exams like GATE also, this unsteady state material balance syllabus is included. So we should also be ready to solve such numericals also, right? So what is the unsteady state process condition? When we say steady state, the parameters within a system are constant. The derivatives of any parameter with respect to time are zero. In that case we call it as steady state process. That is the, for example, density or any parameters, any pressure, temperature do not change with respect to time, then the derivative with respect to time is going to be zero. Such processes are called steady state process. Most of the continuous operation processes are steady state process, whereas if you look at unsteady state process, where it comes across, whatever is batch operation, for example batch distillation, batch reactor, okay, or a semi batch reactor, or even extraction process, batch extraction process, all of them are example for unsteady state process. Sometimes this unsteady state condition is preferred because it has its own advantages, economic advantage or efficiency may be more, right? So there are some advantages associated with unsteady state process also. And even with continuous processes, you are continuously operating at steady state, but you want to shut down the process. During shutdown or during the startup, you have a new plant, then you want to start the process. That case also during this transient phase is there, right? So that way the unsteady state conditions we come across in a chemical industry. Okay, so that way we will come across, even in continuous operation we will come across startup, shutdown and some unexpected upsets. During upset operations we are going to have unsteady state condition prevailing in a chemical industry. Okay, so that way we should able to solve numericals for unsteady state processes also. Okay, what could be a simple example that we can consider at this stage, being in second year of a BTech chemical engineering? So at least we should be able to solve numericals with respect to simple mixing. That is, we have a tank and we have some certain amount, certain volume of liquid solution with a particular solute is present in it. Let me say some X percentage is the solute concentration in a liquid. Then we are sending in something. Say for example, there is an input flow of a particular solution where the concentration of the solute is known. For example, input flow rate and it's the solute concentration is known. So we can continuously send in some amount of input, and there may be some withdrawal of the product also continuously, some flow rate and some concentration. So that way we can write a material balance for a unsteady state system, because here accumulation is taking place. That is, with respect to time there is change in the volume or mass of the substance liquid in the tank, and as well as the concentration of the solute in the tank also getting changed, right? So that way and we are going to have a input, it will have a concentration of the solute, we are going to have output which will have a concentration of output. So this is a general case. So for this we can write a material balance including an accumulation term in it, right? So material balance, so far what we have done without chemical reaction, so input minus output equal to accumulation, we had accumulation term 0. So we always did numericals for total input equal to total output, right? But here we are going to consider input, there is going to be mass flow rate, inflow rate, and there is going to be mass outlet, and there is going to be accumulation. So that way we can write material balance. Also we can write the individual material balance for the solute also, right? Solute concentration in the inlet stream, solute concentration in the outlet stream, and solute concentration in the tank. Okay, so we can solve the general material balance equation. In this there can be some special cases. Say for example, there may be a case where because usually the tank concentration is there, so we can try to keep the keep the total volume in the tank can be kept constant. That is one option is there. That is the initial mass of the tank, and at any time also the mass is going to be the same. So we can maintain mass constant by having same flow rate of input and output, right? That is one option. And we can have a system where the contents of the mixer tank, the contents in the tank are well mixed. So if a tank is well mixed, what is will be the concentration in the outlet stream? If it is like a CSTR reactor, when the contents are well mixed, the outlet stream also will have the concentration within the tank and the concentration in the outlet stream are going to be the same. So that is one option. Okay, and there may be a case where the inlet stream is not having the solute at all, and there may be a case where input and output flow rates are same. Okay, and a tank, so that way we can have a tank volume is kept constant, we can have a tank which is well mixed, we can have a rate of input equal to rate of output, we can have a condition where inlet stream is not having any solute. So for all these cases, the overall material balance and the individual material balance can be simplified. Once we have this simplified general expressions, it is easier for to use those equations to solve the numericals also. Okay, so any numerical we can have, remember the, we can write the general material balance and solute material balance for this unsteady state system, and we should able to simplify it for the given condition and substitute the data to get the unknown parameter. Okay, so that way we will do some numericals on this topic, material balance in unsteady state system. Okay, so we are going to discuss about unsteady state processes or operations. You can say simply system, unsteady state system. Okay, what is the unsteady state system? The operating parameters remain constant with time. That means time derivative of any parameter is 0. So that is an unsteady state process. Okay. And we can give examples for unsteady state operations. If it comes to batch operations like distillation, extraction, batch drying, okay, and even reactors. We say batch reactors. Okay, these are some examples for unsteady state system. Okay, so here they are unit operations, and here reaction is taking place. So even for catalysis, regenerative systems. So these are some of the examples for this one. Even the continuous operations during three conditions, of startup or shutdown or during upset. Under these conditions, we are going to have unsteady state condition even in case of a continuous processes. Okay, so even if a process or operation is continuous system, in a continuous system during initial startup, or if you want to shut down the plant, or if there is any upset in the parameters, then that system may behave like an unsteady state system because the parameters are going to change with respect to time. Okay, so if you are so in these cases, what we can do is, if we consider a small time interval, consider a small time interval delta t, we can find the change in parameters. The change in parameter can be determined by considering a small time interval. If you know, say for example, when time is t equal to 0, and finally we have a t. Okay, so the parameter initially the value was like, say for example, temperature, let me say T1, and here it is T2. So this delta T, during this delta T, what is the delta T can be determined, like, so that way we can determine the parameters by considering a small interval. Okay, so if the simplest example that we can consider is, consider a tank. Okay, so which has some liquid in it, that initially some mass of mkg is there, and let the concentration of the solute in it be x. So that means x is the mole fraction of the mass fraction of the solute. Okay, and what happens, this is having there, it is time t equal to 0. What happens if you are supplying some, there is some feed, let me say small m I input flow rate, this much kg continuously is flowing, let me say kg per minute or kg per hour. Okay, whatever is the unit, so initially kg only there. So similarly there is some output which can be m output this much kg per hour, and the concentration of the solute in the inlet can be x input and it can be x output. Okay, so now we are having uh, let this is the flow rate, this is mass fractions. Okay, so what we can do is we can derive the expression now. This, let us say it is being some mixing is there. Okay, so what we can do is we can write the material balance. So first write the what is this term, let m is the mkg of solution is present in the tank, and x is the mass fraction of solute in it. Okay, let the feed to the tank, let the input or feed, continuous feed to the tank is mi kg per hour. Similarly, let the, and the concentration be xi and x input, and the solute concentration is x input. Similarly, you can write the output or product that is leaving. Okay, the product stream, this is feed stream, product stream from the tank is m naught kg per hour, and solute concentration is x naught. Okay, so what is the input, then what is the input stream? So we have input conditions mi and its concentration xi, output conditions m naught and x naught. Okay, in the tank initially when time t equal to 0, there was a m, there was m comma x. Okay, right, so can we write the, let us consider a time interval delta t. Okay, so if you consider that delta t is the time interval, let the accumulation be dm. So say for example ms become new value, so we can say that new mass is m plus dm, then dm is the accumulation. Okay, if dm is the accumulation, then the new mass will become at time t, in time delta t, that is dm is the accumulation, then at time t what happens, m plus dm is the new mass, and we are going to have some concentration also, right? So this is, and if it is, we should know some what is the new concentration, that will check later. So how to write the material balance, how to write the material balance in this case, overall material balance, the overall material balance is, what is the overall material balance, input minus output equal to accumulation. Okay, so we have accumulation amount we know. Okay, so here the accumulation is dm kg. Okay, so input is, what is the input, input is simply mi dt minus m naught dt equal to dm. Okay, because solution input is this, solution input is in time t how much is the solute has come. Okay, solution input in delta t time is mi into delta t, because what you are multiplying by time only we will get how much kg has came, no, because dm is in kg, So if we know the flow rate multiplying by the time it has taken, then we know what is the input, what is the output, right? So we can say mi dt minus m naught dt equal to dm. Okay, and we can say take it to the right hand side. I can say mi dt is equal to dm plus m naught dt. Okay, this is the overall material balance equation we have to make use of in all the problems. Okay, similarly, what is the individual material balance for solute material balance? That is individual material balance. So what is the solute input? So solute input is, solution input is what? Similarly, here we can write solute input is what? This is the amount of mass and multiply by its mass fraction, right? So we can say xi into mi into dt. Okay, so xi into mi into dt is the solute input. Similarly, solute output is x naught into m naught into dt. Okay, this is the total mass multiplied by mass fraction. Total mass multiplied by mass fraction. And what is the accumulation? In this accumulation also we are going to have, if we have dm m into x, right? So what is the accumulation? Means what is the amount of solute in the accumulation is, so if differential of m is the mass, okay, so you have to have differential of x into m. So this is the solute in the accumulation. So we can substitute this term to get what is the, so we can write xi mi dt is equal to, in this d we are going to multiply by x into m, as m is mass, solute mass is x into m, plus x naught m naught dt, x naught m naught dt. Okay, then this term can be written as two terms, right? Xi mi dt is equal to uv method, right? Udv plus vdu. So x into dm plus m into dx plus x naught m naught dt. So this is our solute balance, individual material balance for solute. Okay, so we will be making use of these two equations to solve the numericals. Okay, so in this case we can have some cases. Okay, as I told you in the introduction, so we can have few cases. So this is our equation, right? So from this equation, let it be the starting point. So we can have different cases, like for example case 1, I can say that tank volume is kept constant. Tank volume is kept constant. So volume is kept constant means what? We using density. We know density equal to mass per unit volume. So mass equal to density into volume. So if volume is kept constant, density is constant, then mass is going to be constant, right? So if tank volume is kept constant, what does it mean? dm is, what is the change in tank volume? It is initially m is the kg, right? So change in mass, there is no change in mass in the tank because tank volume is tried to kept constant. So dm equal to 0, right? So let it be equation number 2. Let it be equation number 1. So what we will have when dm equal to 0? So when dm equal to 0, equation 1 will become mi dt is equal to m naught dt, mi dt equal to m naught dt, and this integer material balance also will get reduced to this dm term will be 0, right? So we are going to have only these two terms. We can write xi mi dt is equal to, first term is 0, so we are going to have mdx plus x naught m naught dt.
Okay. Okay, so this is the condition when we have tank volume is kept constant. That is initial mass of the tank. Whatever is the liquid present, that level is kept constant. Okay, level volume is kept constant. That means mass remains constant. Therefore, dm is equal to 0. So substituting that condition here, we are getting this equation. Okay. Then we have second case. So here, if the tank is well mixed, if the tank is well mixed, what does it mean? When the tank is well mixed, the concentration in the tank and the outlet stream is going to be the same. The concentration in the tank and the outlet stream is going to be the same. So that way we can say that when tank is well mixed, X output is going to be X. That is solute concentration in the output is equal to solute concentration in the tank. With the time also, this solute concentration is going to be the same because well it is well mixed, right? So already if you are apply depending on the condition anyhow. Okay, so if you substitute this condition, what will happen? Go to equation 1 and 2. So equation 1 will become and equation 2. Okay, if the tank is well mixed so that output stream is equal to input stream, then composition of the solute in the outlet stream is equal to concentration of the solute in the tank, right? So that way this equation 1 will become mixi dt, or simply the second equation, at least the solute, what happens to the solute, because in first term what we have is equation 1 is mi dt dm m naught dt. There is no x naught term there. Okay, so that way equation m first term will be the same. Mi dt is equal to dm plus m naught dt. Okay, and second equation is your xi mi dt, xi mi dt is equal to x into dm. We'll have x into dm plus m into dx plus we are going to have x naught m naught d naught. That x naught is equal to x, so we can say x into m naught dt. Okay, so this is the set when the tank is well mixed. Okay, so then we have another case, case 3. So case 3, if the rate of input is equal to if rate of output, if the rates of input is equal to rates of output, that is it is given mi is equal to m naught. Okay, so if mi is equal to m naught, then what will happen to the first equation number 1? Equation 1 will become, that is overall material balance will become same m into, instead of mi we are going to write m, because mi equal to m naught equal to m. That's what we are going to substitute. So we can replace the I term and O term from it. So m into xi dt is equal to x into dm plus m into dx plus x into m dt. Okay, xm dt. Okay, now another case 4. Case 4 is if all the above 3 are there. So this is the equation. What happened to the second? This is second equation will become. What will happen to first equation? First equation is m dt equal to dm plus m dt. mdt equal to dm plus mdt. dm plus mdt, which means dm equal to 0. Okay, so we have 6 and 7 being the condition when the rate of input equal to rate of output. When rate of input equal to rate of output, accumulation is going to be 0, right? And this input flow rate and output flow rate are equal to a common flow rate m. Okay, so that can be substituted if all the three above coexist. So in that case, what will happen? So we are going to have dm equal to 0. Okay, mi equal to m naught equal to m. Okay, and x output equal to concentration of x in the solute in the system. If we substitute all the three, what will happen to equation 1 and 2? Okay, so what we are going to have is, what is the first equation? Mi dt equal to dm plus m naught dt. So this is auto justified, this gets cancelled, right? So we have mi dt equal to m naught dt and dm is 0. So this is equal to 0. Total term is vanishing. Okay, what about second equation? The second equation is m into xi dt is equal to mx dt plus m into dx. This x into dm term will disappear. Okay, so that way we are having equation number 8 for this condition where tank liquid level is kept constant, liquid volume is constant, input flow rate is equal to output flow rate, and well mixed. The constituents in the tank are well mixed, means outlet concentration, outlet solute concentration is going to be equal to the concentration of solute in the tank. Okay, so in that case you will have an expression of 8. Okay, so we are going to make use of these equations, so please learn to write these unsteady state and steady state equation. Okay, so what we did, we assumed initial volume of m and x with the solute concentration, and in a small delta t, what is the amount of input, what is the amount of output we considered. We wrote the overall material balance and we consider the solute concentration, individual material balance. So these two equations can be simplified for case 1, where the tank volume is kept constant, case 2 where the tank is well mixed, case 3 where the rates of input is equal to rate of output, and all three together we had a condition. And apart from all these, we have one more case, where case 5, where inlet stream has no solute. That is inlet stream, that is input stream is xi is equal to 0. Okay, so in this case, what will happen to these equations? We have to see. Okay, when the solute is absent in the inlet, what will happen? This equation, equation 8, in addition to the above, if inlet stream has no solute, this term will become 0. So what we will have is mx dt is equal to m into dx. Okay, so this expression can be separated, and dt equal to dx by x. Okay, so this equation integrating between the limit 0 to t, let the concentration varies from x1 to x2. Okay, so we are going to have t is equal to m by m integral x1 to x2 dx by x. Okay, so this is equal to m into t. M into t is the mass of input flow, mass of input, whatever it may be. If it is water, let me say water, in time t. Okay, this is the total amount of water added in time t. That way you can say if it is kg per minute multiplied by minute, you'll get this much minute, right? So that way you can write mt is equal to capital M, which is the volume of the tank, into ln of x2 by x1. Okay, so the amount of water to be added can be mt equal to m into ln of x2 by x1. Okay, sometimes minus sign will come into picture, which can be further simplified. Hmm? Now itself is it there coming x equal to mx dt, mx dt is equal to m into dx. So we are having mx equal to dt. Okay, no, I think some minus sign was there, right? Yeah. So this mx dt equal to minus dx. This is going to opposite side. Let's say this minus sign will be present. Okay. So thereby we can change the limit also. Okay. So what we have is m dt is equal to minus m into ln of x2 by x1. So out of these parameters, how many parameters are there? Small m, t, x1, x2, m. Out of these 5 parameters, 5 variables are there. Out of these, if 4 are known, we should be able to find the one unknown parameter. Okay, so that way we will solve some numericals. Okay, let us consider this problem. Take down. A tank contains 100 liters of salt solution in which 5 kg of salt is dissolved. Water flows into the tank at the rate of 5 liters per minute, and the salt solution leaves the tank from the top at the same rate. That means input rate is equal to output rate. Due to complete mixing, the concentration of salt in the tank is uniform all the times. So what is the indirect information? The outlet stream will have the same concentration. Find the amount of salt remained in the tank at the end of 50 minutes. When t equal to 50 minutes, what is the amount of salt remained in the tank? Take the density of the salt solution as 1 kg per liter. Okay, like water. They are asking us to consider to be water density 1000 kg per meter cube, which is 1 kg per liter. Okay, so here the given data you can solve the problem. Okay, it's given that a tank contains 500 liters of salt solution, right? So we can say initially we have a tank where we are maintaining 100 liters of solution, and then we have a feed which is 5 liters per minute, and it is given that outlet stream is also 5 liters per minute, and salt solution is leaving, in which 5 kg of salt is dissolved. This is initially containing 5 kg of salt. Okay, this 100 liters means what? Given 100 liters, what does it mean? It is given density. You can take the density to be 1 kg per liter. That means this is equal to 100 kg. So this is our basis. Our m is our basis. Okay, we want to keep m equal to 100 kg. Okay, other data given are find the amount of salt remain in the tank when time t equal to 50 minutes. What is the amount of salt? Okay, so that we can determine. That means once we know the x value, x into m is equal to amount of salt. Okay, at time t equal to this. Initially the salt is 5 kg. At 50 minutes, what is the amount of salt? Okay, so that is going to be changed. And water flows into the tank. That is, water is flowing. That means it is giving us an information whether water is containing the water is coming. That means the concentration of salt in the feed, that is xi is equal to 0 in our case. Okay, so those are the some of the information we infer from the given data. So I'll write them here for our understanding. So we have mi equal to 5 liters per minute. Okay, and we have m naught is equal to 5 liters per minute, and we have xi equal to 0, and we have x not equal to x in the tank. Okay, because it is given that it is well mixed. Okay, at time t equal to 50 minutes, what is the x value? So that's what we should divide, x value and amount of salt we have to find out. Okay, density was given which we have used. So at any time t, let us consider at any time t, let the concentration of salt is x, that is mole fraction of the mass fraction of the salt is x in the tank. Okay, then initially when time t equal to 0, we have a condition. Time t equal to 0, the x value was 5. When t equal to 50 minutes, right, when t equal to 50 minutes, what is the x value? So that is our question. So integration limits we have. Okay, so let us look at what is the input. What is the input stream here? What is our input? Our input is equal to mi, which is 5, which is 5 kg per minute, right? Mi is 5 kg per minute. Okay, and what is the amount of salt in the inlet stream? Amount of salt solution in the tank. Let us say what is the amount of salt solution in the tank is given that 100 liters initially. We can tell that also in terms of 1 kg per liter, which is equal to 100 kg, which we have determined earlier also. Okay, so this is the amount of salt solution. Okay, so input is equal to, it was given that 5 liters per minute multiplying by density, which is 1 kg per liter. So we get 5 kg per minute as the inlet stream. Similarly, amount of salt solution in the tank is total solution, it is okay 100 kg, and it is having that initially it is given that 5 kg of salt is present. Okay, so let it be there. Let delta x be the change. Let in delta t time, in let in delta t time, let delta x be the change in the concentration of salt in the tank. Okay, change in concentration of salt in the solution present in the tank. Okay, so we have delta x kg of salt. Initially, what is the kg? Initially there was 5 kg of salt, then there is delta x kg of change is there. So we have to find what is the delta x value, right? What is the salt input? As I said earlier, inlet stream is not containing any water, that way xi is 0. Okay, so salt input to the tank, will say when I write the salt balance, if it is present also, what how we will proceed is, we will write salt input to the tank. In our case it is 0, directly we are writing. Okay, because it is pure water which is entering the system. Whereas if it is having some solute, how we will determine is, whatever is the given concentration, let me, here it is 0 into total mass, right? Mass is, you have 5 kg per minute. Just for unitary I am doing this, 5 kg per minute into time, in time t, this is a mass, this is the amount of solute concentration. That's what we did in derivation also, right? So we calculated mi dt and then xi. In our case xi is 0, so this term is not having any meaning, but just for unit tally I am showing this. So what we will get is this much kg, but in our case it is 0 kg because xi is 0. Since xi is equal to 0, we get 0 here. Okay, So if it is not xi, we are going to get the corresponding value. For example, even if it is 0.01, you have to multiply by 0.01, so into 5. So 1% of 5 you are going to get. Okay. So that much kg we will get as the input. What is the salt output? Salt output from the tank is equal to same way, right? X into what is your output? Again 5 kg per minute in delta t time minute. Okay, so we get this much 5x. Is it 5x? What x is given? Okay, let x by 100 is a fraction. 5x by 100 into delta t, and this much kg we get. Okay, so this is the salt output. 5x delta t by 100, which is 0.05x dt. Shall I write or delta t? Okay, when we are integrating, we'll write it as dt. Okay, so this is one input and this is one. Let it be a, let it be b. And if you make a solute balance, is it input equal to output? No, because it is unsteady state. So we will write input, salt in input minus salt in output equal to salt in accumulation. Okay, so we know that accumulation amount is del x is the kg of salt is accumulated in time del t. That's what we have considered. We have considered it. Del x kg of salt is accumulated in del t time. We are writing generally. Finally, we will substitute the delta t time. Okay. So del x is the kg. Inlet is 0 kg minus outlet is 0.05x del t equal to this much, right? So now we can simplify this, rearrange this expression to be del x by x equal to minus 0.05, right? So this is the general expression we have now. We can simplify it to get the final answer. So what is that? Integrate it. We can write it in the terms of dt, right? So we can write like minus 0.05 dt from 0 to t is equal to dx by x integral x1 to x2. Okay, so our x1 value is 5. Okay, and our final value we don't know. Okay, this much kg. Now x is in kg, that's why it is x kg. We are going to get x2 kg. X2 is the unknown here, and t0 time t we have x1. When time t equal to 55 minutes, what is the value of x? Okay, so can we integrate it and get the answer? Minus 0.05 integral dt is t varying from 0 to 55 minutes. With the unit you have to do. Okay, this is going to be ln x varying from x1 is 5, we don't know x2. Okay, is equal to ln x2 by 5 equal to 55 minus 0 minus 0.05. Okay, so simplify it to get the answer. What is the value? So the 5% of 55 is 2.5 equal to ln x minus ln 5. Okay, so ln 5 value is 1.61. So you can rearrange it to write what is ln x. 0.891 and x is equal to e power minus 0.891. You get x equal to 0.41 kg. So the solute going to be present is equal to 0.141 kg. So x is, what is the x? This is the kg of solute in the tank at t equal to 55 minutes. So x equal to 0.41 kg. That is our answer. Okay. So you can solve another problem. It's a gate problem. A tank initially contains 500 kg of an aqueous solution of 10% salt. How much water must be fed to the tank to reduce the salt content to 1%? The contents of the tank are thoroughly mixed and the mass in the tank is maintained at 500 kg by keeping the continuous feed and drain streams at equal rates. Okay, this is similar to previous problem. You should try to solve it on your own and please comment your answer. Okay. Okay, what is given in this problem? A tank initially contains 500 kg of aqueous solution in 10% salt. So that way x is given. X initially is when time t equal to 0, x is 0.1 is given. And what will be the time? We are going to have a time any time t, we will have the concentration to be 0.01. Okay, this is given that inlet streams and outlet streams are equal. That means dm equal to 0. And it is given that mi equal to m naught. Mass flow rate is inlet and outlet are equal. It is given. Okay. So now what we can do? We can draw a diagram. Okay, we can draw a diagram. Inlet stream mi xi m naught x naught m and x. Okay, and it is given that 500 kg. And it is maintained. This is our basis now. 500 kg is our basis. Okay, and what is our interior material balance? General material balance we can write mi xi into dt is equal to m naught x naught into dt plus x into d into xm, differential of xm. So we can write as it as m naught x naught dt plus x into dm plus m into dx. So this is our expression. Okay. X naught into midt. Okay, this I am writing this way so that you know that it is solute balance. Okay, so we have a solute balance like this, and we are having a condition where Tm equal to 0, xi water is pure, and we have mi equal to m naught equal to m. Okay, so these conditions we can substitute dm equal to 0 xi, and what is x naught value, and it is given that it is well mixed, therefore output is going to be equal to whatever is the well mix. Okay, so based on these conditions, in this term what will happen is this dm term is 0, your mi equal to your xi is 0, that is getting cancelled. Okay, so this equation x naught will become x, mi will become m. Okay, so we have xm dt plus m dx equal to 0. So therefore you can say that x into m dt equal to minus m into dx Therefore, m into integral dt is equal to minus m dx by x. Okay. We have a time t equal to 0, x equal to 0.1, and at a time t we have x equal to 0.01. So basically from 0 to t, 0.1 to 0.01, we are going to integrate this expression. So integrating from m into 0 to t dt is equal to minus m into dx by x, 0.1 to 0.01. So integrate this. So you can write, what is the integration limit here? You have integration limit of when time t equal to 0, x equal to 0.1. When time t equal to t, at a time t, x equal to 0.01. Okay, so the limits are 0 to t and 0.1 to 0.01. So if you integrate the left hand side, m into 0 to t dt is equal to minus m into, what is that, integral dx by x? That limits will be 0.1 to 0.01 dx by x. So we can get mt in the left hand side equal to minus m into ln of x with limits from 0.1 to 0.01. So taking into the minus, into minus can be used to change the limits. So we have m into ln of 0.1 by 0.01 equal to mt, and this is mt is the amount of water to be added. So we have f value given is 500 kg, and ln of 0.1 by 0.01 is 2.303. So we get the value of 1151.5 kg as the amount of water to be added. Okay, why mt term, we can check the unit. Okay, m is kg per minute and t is the time taken. That only will give us the amount of water to be added. So the amount of water to be added to the system is 11.5, so 1151.5 kg. Okay, and so if you remember the general equation, and what is our general material balance equation? Xi into mi dt my equal to x naught into m naught dt plus accumulation term. What is the accumulation term? X into differential of x into m, right? So if we remember this expression, we can solve any problem. Okay, so depending upon the simplifying the equation to any given form. Okay, so we should, but one more thing we should know is that differential uv is udv plus vdu. That means we are going to have two expressions, that is x into dm plus m into dx in the right hand side. Okay, so depending upon the given conditions, we may simplify the expression. Okay, so that way it's important to able to write this unsteady state material balance for solute. So if you are able to write this, you'll able to solve the problems. Okay, so now please practice this problem yourself. A tank contains 1000 kg of a 10% salt solution. A fresh stream containing salt at 20% salt solution enters the tank at 20 kg per minute, and the mixture leaves the tank after complete mixing at a rate of 10 kg per minute. Express the salt concentration as a function of time. That is the first part. Derive an expression by writing the individual material balance for the solute. At what instant of time salt concentration will be 15%? So you have to find the time given x value. Then last part, what will be the salt concentration in the tank after 2 hours? Okay, so as we did two numericals, please follow the same procedure. So first write the given data. So here at time t equal to 0, we have m equal to 1000 kg, and the concentration of solute x value is 0.1. Okay, we have an inlet stream where mi is equal to 20 kg per minute, and xi is also given 20%, so xi is 0.2. We have output stream m naught, which is 10 kg per minute, and we don't know what is x naught, but it is given it is well mixed, right? The mixture leaves the tank after complete mixing. That means x is equal to x naught is equal to x. Okay, so that we have, and we have time t equal to 0, we have x naught equal to 0.15. Okay, at what time t, at time t equal to 2 hours, that is 120 minutes, what is the x value? Okay, so we can write the overall material balance and individual material balance and solve this problem. Okay, okay, solve this another problem. A storage tank contains 10,000 kg of a solution containing 5% acidic acid. A fresh feed of 500 kg per minute of pure water is entering the tank and dilutes the solution in the tank. The mixture is stirred well and the product leaves the tank at the rate of 500 kg per minute. At what instant of time will the acid concentration in the tank will drop to 1%? So here capital M is given 10,000 kg and x value, initial x value is given 0.05. 50% means 0.5, 5% means 0.05. So initial, when time t equal to 0, x value is 0.05, and finally what is the time when x value becomes 0.01? Final percentage is 1%. 10% means 0.1, 1% means 0.01. So x value time integration limits are here 0.05 to 0.01 when time 0 to t. The t you are going to determine, and mi input flow rate, mi is equal to 500 kg per minute, and m naught is also given, m output also given 500 kg per minute. Okay, and pure water is entering, that means xi is 0 and x output is going to be equal to x in the tank because it is tank is well stirred. Yeah, you can solve this problem now. Okay,
Comment your answers. If you have any doubts, please contact me. Thank you for joining my classroom.